Mr. Thompson here again. All right, page 59. We're working on questions 3 to 7. Unit 3, electromagnetism. We're studying the force on a moving charge in an external or in a magnetic field. Okay, question number 3 says the magnitude of the acceleration of a proton is 5 times 10 to the 14 meters per second squared. If the magnetic field strength is 400 milliteslas, then what is the proton's speed? Okay. So we've got the following. Fm is equal to Fc. We can equate the two. This is going to be Q times V perpendicular times B, which is equal to M times AC. Solve this equation for V. V perpendicular is going to be M times AC over Q times B. Now the mass of a proton, 1.67, E negative 27. The centripetal acceleration, 5.0, E 14. Divide that by Q for a proton, 1.60 exponent negative 19. And the magnetic field is 400 milliteslas. Okay, and the calculation, gentlemen. All right. I get 1.3 times 10 to the 7, it looks like. 367. Moving along, question number 4. An alpha particle enters a perpendicular 75 millitesla magnetic field at a speed 3.9 times 10 to the 5 meters per second. Is the motion clockwise or counterclockwise? Okay, we're going to use our third right-hand rule for force. Why are we using the right hand? It's because it is a positive charge. It's an alpha particle. It even shows the charge right here, okay, going in the diagram into that magnetic field. And so we use our right hand. What we do is we point our thumb. Make sure your thumb is pointing to the right because that's the speed, right? And now the magnetic field has to be going out, and so the only way to do this is to point your fingers kind of out of the page towards yourself, your thumb pointing towards the right, and then your palm faces down. And so the force at this point, the magnetic force as it enters, should be downwards. And so what will it do here? Well, it's going to do the following. It's going to start curving downward, and it's going to end up rotating around in this fashion. What do we call that? Clockwise or counterclockwise? It should be clockwise, okay? In B, what is its acceleration when it first enters? Now we can go ahead and set up our equation that we used in the last, just a moment ago in question 3. Fm equals Fc. We have Q, V perpendicular times B is equal to M times AC. And now we're going to solve for AC. AC is going to be QV perpendicular B divided by the mass. And AC coming down here, we've got 3.2 E negative 19. The speed, 3.9 E5. The magnetic field strength, 75 E negative 3 milliteslas, divided by the mass, 6.65 E negative 27. And the calculation, please. All right, I got 1.41 E12 All right, what's the radius of curvature? Now in part C, we can introduce something new that we've been working on, okay? But we can just substitute in a little bit more to the expression. And so this is going to be Q, V perpendicular B. Over here we've got M, V squared over R. You notice V is on both sides. Both V's are the same. And so what I can do is I can cancel off a power of V, okay, and this, and I can solve it for R. We do the old Thompson switcheroo. So R comes up to the QV side, QB goes back down. And it makes this kind of, I don't know, sing-song final version, which is MV over QB. Rhyme to it. Okay, so we've got the alpha particle's mass, 6.65, E negative 27. We multiply that by the speed, 3.9, E5. We divide that by Q. And the magnetic field strength of 75 milliteslas. The calculation. All right, I got decimal 108, which would be 10.8 centimeters. All right, let's take a look at question number 5. An electron is traveling at a velocity of 1.88 times 10 to the 7 meters per second towards the west. If the magnetic force on the electron is 1.37 times 10 to the negative 12 newtons directed vertically upward, what is the magnetic field? Okay, so let's draw a diagram of what's actually happening here. It's traveling towards the west, so the electron's moving this way, okay? We have the force directed vertically upward, and so if we think about our compass points like this, right? You got north here, you got south, you got west, you got east, so I set the first part up correctly. But then when you have up and down, then up is going to be like this, and down is going to be like this. Okay? And so if the force is directed vertically upward, then that means that the force has to be that direction. Okay? Now what I'm going to do is I'm going to use my third left-hand rule for force. Why my left hand? Because it's an electron moving. So my thumb is going to be pointed towards the left. The force should be out of the page. So what direction would the magnetic field be? I have the magnetic field essentially going towards the north, okay? Because when you have your hand oriented, I'm just trying to give you the visual here, thinking about drawing it, it'll look like this, okay? Here's your fingers pointing this direction. And so you have the electron going that way, you have the force, which shows your palm going out this way. So here's your current, here's your force, and then the B field has to go that direction. Now that direction, if you take a look at the diagram here, corresponds with north, okay? Sorry about the delay on that one. Just trying to make sure I'm doing a quality job there. Question number 6. A particle with 7 electrons is in excess enters a perpendicular 300 millitesla magnetic field at a speed of 4 times 10 to the 6 meters per second. If the diameter of its motion is 14 centimeters, determine its mass. Okay, so a lot of these questions involve, when you equate FC and FM, making sure that you're solving for different variables. And so this is Q, V perpendicular times B. This is mv squared over r. I want to solve this for m. M is going to be, well, QBR over V. Plugging in my stuff. 7 electrons, so the charge is going to be 7 times 1.6 E negative 19. The magnetic field strength, 300 E negative 3. Now the radius here, not the diameter. If the radius is 7 centimeters, then the diameter is 14. So we're going to use 7.0 E negative 2. And then we're going to divide that one by V, which would be 4 E6. All right, I got 5.88 E negative 27 kilograms. Okay? And last one. Let's just wrap this up, everybody. Question number 7. A Physics 30 student performs an experiment with an electron moving in a perpendicular external magnetic field. He varies the magnetic field and measures the effect on the resulting acceleration. All other variables, including the speed of the electron, are held constant. Sketch the straightened curve showing the relationship between the two variables, state its equation, determine the significance of the slope, and provide the units for the slope. Okay, so notice in the experiment here, you want to figure out what is the manipulated variable, what's the responding variable, what is the equation that works with this, okay? And so what you have here is you have essentially an electron that's exhibiting an acceleration because of a magnetic force. And so Fm is equal to Fc would be a great way to set this up, okay? You can put Fn equals Ma if you'd rather, okay, which is just F net. So this, you could also just do this, right? Instead of the AC, then you can just put A for the acceleration. So if I go with this version right here, then this is how the equation works, okay, or looks to start. And now what I'm going to do is I'm going to realize what's the manipulated variable, what's the responding variable. The manipulated variable is going to be the magnetic field. The responding variable is the resulting acceleration. Now we solve this one for the responding variable. So the responding variable is acceleration, so solve for the responding variable A. A is going to be Q, V perpendicular V over M. Still another one of these direct relationships, because when you set this one up so you can see what the slope is, it's Q, V perpendicular over M. That all multiplied by B. This is now like your Y. This is going to be equal to your slope. This is going to be your X. Okay? So it should make a graph, as you can imagine, that's going to have the manipulated variable B down here, the acceleration, responding variable here. It's going to be another linear equation. Okay? However that happens to look. Now the slope, of course, is equal to Q, V perpendicular over M, and the units. Now there's two ways to do the units. I ran out of time last time. I'm also going to run out of time here, but the units can either be based on the graph, which would be meters per second squared over magnetic field strength. That's like rise over run, okay? Which ends up being a meter over second squared times Tesla. Or what you can do is you can look at Q, V perpendicular, and M. So if I have a chance to do that, let's try it. Or Q is coulombs, V is meters per second over kilograms. Okay? And so that would be coulombs times meters over seconds times kilograms. All right, thank you very much. I'm going to call it done for the moment.